This investigation looks at how certain 19th-century street lighting systems functioned in dense cities without relying on a centralized electrical power plant, long before modern grids became standard. The subject matters because physical remnants of these systems still exist in urban architecture, yet their operation is often reduced to oversimplified explanations. By examining surviving infrastructure, archival records, patents, and period engineering limits, the goal is to clarify what these lights actually were, how they worked in practice, and why they seem puzzling today. Rather than offering hidden causes or dramatic theories, the focus stays on evidence that can be observed, documented, and logically reconstructed. At first glance, street lighting feels inseparable from centralized power. We are used to the idea that light arrives from distant plants, routed through grids too complex to notice. Most viewers also know that 19th century cities did not yet have those systems. Gas lamps, manual labor, and localized solutions filled the gap. What unsettles people is encountering records of streetlights operating before large power stations became common. That detail raises questions, but it does not require abandoning reality. Instead, it invites a closer look at how infrastructure was actually built and supplied at the time. This investigation treats those streetlights not as anomalies, but as engineered systems shaped by practical limits, local needs, and the technologies available then. Understanding that context is the first step before asking larger historical questions. Most historical accounts explain early street lighting through a combination of gas systems, experimental electric lamps, and small-scale local generation. In the 19th century, cities already operated extensive gas networks designed for heating and illumination. Pipes ran beneath streets, feeding lamps that were reliable, serviceable, and well understood by municipal engineers. When electricity began to appear, it often entered this existing framework rather than replacing it outright. Early arc lamps and incandescent systems were powered by nearby generators, sometimes housed in basements, workshops, or municipal buildings. Because these installations were limited in reach and short-lived, historians frequently grouped them together under broad labels like gas lighting or primitive electrics. That simplification serves a purpose. From a distance, the dominant story remains accurate. Gas-lit most streets and centralized electric grids came later. Records, budgets, and maintenance logs support that narrative, making it sufficient for general history. It explains how cities were illuminated, how costs were managed, and why transitions occurred when they did. For most audiences, there is no need to separate every variation. Yet, within that accepted explanation sits a range of localized solutions that rarely receive detailed attention. Recognizing this does not challenge the mainstream account. It simply prepares us to look more closely at what those early systems actually involved. That added detail becomes important once physical evidence is examined, rather than assuming every lamp followed a single, standardized model across all cities and decades uniformly. What complicates the simple explanation is what still exists in older cities today. Surviving streetlight poles, underground conduits, and mounting hardware reveal details that written summaries often overlook. Some poles contain internal channels inconsistent with gas-only delivery. Others show evidence of insulated wiring paths, access panels, or base housings designed to protect mechanical components. In several locations, the distances align more closely with electrical series circuits than with gas pressure requirements. Looking carefully means paying attention to construction, not decoration. Cast iron bases, reinforced collars, and sealed compartments suggest equipment that required protection from moisture and vibration. In certain streets, remnants of conduits appear too narrow for gas volume, yet well suited for electrical conductors. These observations do not prove a single system, but they narrow the possibilities. They tell us what could not have worked. The value of this evidence lies in repetition. Similar pole designs appear across different cities and decades, often modified but structurally related. This consistency indicates standardized engineering solutions rather than improvisation. Importantly, these features remain visible to anyone willing to look closely. They are not dependent on lost blueprints or fading photographs. By grounding the discussion in materials, spacing, and construction choices, the investigation moves from abstract claims to physical constraints. That shift changes how the question itself is understood. This approach also explains why casual observation misses the pattern. Individually, each pole looks ordinary. Together, they form a system. Once attention is directed to uniform heights, repeated junction points, and protected interiors, the infrastructure begins to read differently. These are not decorative flourishes. They are functional decisions. They reflect engineers anticipating current flow, maintenance, access, and failure points. Architecture, in this sense, becomes a technical document. It preserves decisions long after the paperwork disappears. That persistence allows modern observers to reconstruct intent without speculation, relying instead on form, repetition, and constraint rather than assumption or inherited narrative. When attention shifts from surviving hardware to paper records, the picture becomes clearer. 19th century patent offices were flooded with applications describing arc lighting systems, series circuits, induction-based regulators, and compact generators intended for neighborhood-scale use. These documents are specific. They describe current limits, lamp spacing, mechanical wear, and safety concerns. Municipal archives reinforce this picture. City council minutes, lighting contracts, and maintenance budgets regularly reference electric arcs, dynamo room, or experimental circuits serving defined streets or districts. Engineering journals of the period treat these systems as practical problems rather than curiosity. Articles discuss carbon erosion rates, voltage drop along short runs, and the difficulty of keeping arcs stable in changing weather. The language is measured and technical, focused on performance rather than spectacle. Importantly, engineers assumed readers understood that power sources could be nearby, distributed, and temporary. Modern summaries often compress this material into a single transition from gas to centralized electricity. In doing so, they omit the intermediate phase where cities tested multiple configurations simultaneously. The documentation never disappeared, but it stopped being quoted. By returning to patents, contracts, and journals, the investigation relies on contemporaneous voices rather than retrospective interpretation. That record establishes legitimacy not through theory, but through the mundane details of procurement, repair schedules, and operating limits recorded at the time. Many contracts even specify lamp counts, nightly operating hours, and penalties for outages, indicating systems expected to function consistently rather than experimentally. To understand how these streetlights worked, it helps to think smaller than modern systems. Many installations relied on localized generation rather than distant supply. Mechanical generators, driven by steam engines or water power, produced electricity on-site or nearby. That output fed series circuits, where lamps were connected in a single loop, so the same current passed through each arc. This design reduced wiring complexity, but created vulnerability. If one lamp failed, the entire circuit could be disrupted. Arc lamps themselves were demanding devices. Carbon rods burned away and required constant adjustment to maintain a stable gap. Regulators attempted to compensate, but performance varied with weather, vibration, and load. Transmission distances were short. Voltage dropped quickly, limiting how far power could be sent without unacceptable losses. These systems also consumed significant fuel relative to light produced. From a modern perspective, the absence of a central plant makes these lights seem inexplicable. In reality, the plant was simply small, local, and often temporary. Power sources were embedded into workshops, basements, or utility buildings that no longer exist. Maintenance demands, noise, and cost made expansion difficult. Understanding these constraints clarifies why the systems worked, why they appeared unusual later, and why they were eventually replaced rather than expanded. Output levels were modest, usually measured in watts per lamp, sufficient for visibility but not abundance. Engineers accepted flicker, downtime, and frequent servicing as normal trade-offs. Because grids had not yet standardized, every installation was custom. That flexibility allowed early success but prevented scalability. As cities grew, these limitations became decisive. What once functioned adequately on a single street could not support entire districts reliably. Economics reinforced this boundary. Central stations eventually offered consistency, quieter operation, and shared maintenance. The earlier systems were not failures. They were transitional solutions optimized for a moment that did not last. Seen this way, their logic becomes clear, grounded, and historically proportionate. They illuminate limits as much as ingenuity, period. In several industrial cities, these lighting systems moved beyond trial and into everyday use. Municipal records from cities like Paris, London, New York, and smaller manufacturing towns describe electric streetlights installed near factories, rail terminals, bridges, and civic buildings. These were locations where bright, reliable illumination mattered most, and where fuel, water, or mechanical power was already available. In many cases, generators were placed inside nearby workshops, pumping stations, or railway facilities, eliminating the need for long transmission lines. Main streets and commercial corridors sometimes adopted similar arrangements. A short run of arc lamps might illuminate a central block, while surrounding streets remained gaslit. Contemporary reports describe regular nightly operation, scheduled maintenance, and contractual performance expectations. These were not demonstrations meant to impress visitors. They were working installations intended to improve safety, visibility, and economic activity. The pattern is consistent across locations. Power was generated close to where it was consumed, often shared with existing machinery. This proximity reduced losses but locked systems into specific sites. When factories closed or relocated, lighting systems often disappeared with them. What matters is that these lights functioned as part of everyday urban life, even if briefly. Their limited footprint does not make them imaginary. It places them firmly within the practical, incremental experimentation that defined 19th century infrastructure development, grounded in necessity rather than spectacle. Contracts often specified lamp counts, operating hours, and penalties for outages, showing municipal confidence in routine performance. Newspapers treated these lights as improvements, not marvels, focusing on reliability and cost. Across regions, the same pattern appears: limited scale, real service, and clear documentation. This consistency across cities confirms these were established solutions, briefly successful before broader systems overtook them. They belong to normal urban history, not exceptional secrecy, and were documented as such at the time period. The decline of these systems did not require hidden motives. Economics alone explains much of it. Local generators consumed fuel constantly and demanded skilled operators. Arc lamps required frequent servicing, replacement parts, and careful adjustment. As installations multiplied, costs rose faster than benefits. Central stations changed that balance by spreading expenses across many users. Maintenance complexity also mattered. Distributed systems depended on site-specific conditions. A factory closure, labor shortage, or mechanical failure could darken an entire street. Cities seeking reliability favored fewer points of failure. Standardization offered that advantage. Uniform voltages, interchangeable parts, and predictable performance simplified planning and budgeting. Scaling exposed the limits. What worked for a block failed at district level. Transmission losses, noise, space requirements, and staffing multiplied quickly. Central grids reduced duplication and allowed expansion without rebuilding every component. Over time, municipalities replaced older systems because newer ones performed better under growing demand. Nothing here suggests erasure. Technologies were superseded, not hidden. Once removed, their infrastructure was repurposed or forgotten, leaving fragments behind. The disappearance reflects progress, choosing efficiency over variety, not a deliberate removal of inconvenient knowledge. Financial records show clear trends. Fuel prices fluctuated, labor costs increased, and municipal budgets favored systems that scaled predictably. Centralization reduced risk and simplified governance, making decisions easier for administrators. Over decades, practicality outweighed novelty. This process was gradual, documented, and unremarkable by contemporary standards. It followed incentives, not secrecy, and left behind only what was no longer useful. That context explains absence without speculation and frames the transition as normal technological selection across industrial cities, period. Whenever unfamiliar infrastructure appears, speculation follows. Streetlights that do not resemble modern systems invite claims of free energy or unknown power sources. Those ideas usually grow from a reasonable impulse. People sense something important existed and want an explanation that matches the scale they imagine. What matters here is narrowing possibilities without dismissing curiosity. Historical records show power always came from identifiable sources, even when those sources were local, temporary, or poorly documented later. Figures like Nikola Tesla are often drawn into these discussions. In period documents, Tesla worked on transmission, motors, and efficiency, not unlimited generation. His experiments were bounded by materials, funding, and measurable output. Treating him accurately helps reduce confusion rather than fuel it. Exaggerated interpretations often arise when context disappears, when generator rooms are demolished and maintenance logs forgotten. Only the poles remain. That gap invites imagination to rush in. The role of evidence is not to scold that impulse, but to discipline it. By tracing wiring paths, contracts, and output limits, explanations become smaller, clearer, and more convincing. Curiosity survives, but it becomes anchored. This approach respects intelligence while closing doors that history never opened. It also restores proportion. These systems were impressive for their time, but they operated within ordinary physics and budgets. Recognizing that boundary allows interest without inflation and appreciation without myth, keeping inquiry productive rather than drifting toward conclusions unsupported by the record. One lesson from these systems is that technological progress rarely moves in straight lines. Cities adopt tools that solve immediate problems, then abandon them when conditions change. A solution can be effective, documented, and widely used, yet still disappear once economics, scale, or priorities shift. That does not make it fraudulent or secret. It makes it contextual. Looking at old infrastructure reinforces this point. Poles, conduits, and mounting hardware act as records when paperwork fades. They show choices made under specific constraints. Studying them encourages attention to evidence rather than stories repeated without examination. History becomes something measured, not inherited. Forgotten technologies are common, especially in periods of rapid transition. Steam, gas, and electricity overlapped for decades. Many systems were optimized for moments that did not last. Recognizing this normalizes disappearance. It also sharpens critical thinking. Instead of assuming suppression or loss, viewers learn to ask what changed, who benefited, and what scaled better. That habit respects curiosity while keeping it grounded. The result is a clearer relationship with the past, built on continuity and limits rather than surprise. This perspective reduces tension between skepticism and trust. It allows doubt without rejecting evidence and openness without exaggeration. When history is approached this way, complexity replaces suspicion and understanding grows without needing hidden narratives to fill gaps left by time alone. By the end of this examination, the streetlights no longer appear unknowable. Something real existed, built by engineers working within the limits of their era. The reason it feels mysterious today is not concealment, but distance. Context faded as systems were replaced and documentation condensed. What remains are fragments that require careful reading. Reframing the question from "no one knows why" to "the explanation became obscured" changes the tone entirely. It invites investigation rather than suspicion. These lights worked because they were practical for a time, not because they defied known principles. Seeing them clearly encourages a different way of looking at old infrastructure. Poles, conduits, and foundations become clues instead of symbols. With attention and evidence, the past becomes legible again, not dramatic, but understandable. This approach respects curiosity without feeding anxiety. It replaces wonder built on absence with understanding built on presence. When limits are acknowledged and choices explained, confidence follows. The listener is left informed, not unsettled, and better equipped to recognize similar patterns elsewhere.